Alright, so now it's time to get you guys coding. So the first thing that you're going to do is work on instruction decode logic. So we've given you some starting point code that includes a program counter that is perpetually incrementing. You probably see in the visualization that the program counter, if you just keep stepping through, will continue on past the branch and just keep incrementing off the end of the program. This program counter indexes into the instruction memory to grab the instruction and provide it for the decode logic, and that's where you'll start off. So you're given this instruction signal that's 32 bits, and we have a couple labs for you to do to decode that instruction. So a couple different labs involving instruction decode. The first lab is to decode the instruction type. And for our machine, our CPU, we're not going to implement the full functionality of a RISC-V CPU. We're just going to implement enough functionality to be able to execute our simple program. And our program is written entirely with 3 instructions: an add instruction, an add immediate instruction, and a branch instruction. So those are the only 3 instructions that we really need to support in our instruction decode logic. This is the table of instruction types based on the opcode from the instruction for RISC-V. And we can simplify things since we only need to support these 3 instructions. So instead of interpreting this entire table, if you look at the instructions that we need, we can actually just interpret based on the row that we're on. So the first row here we can decode as an I type, and the next 2 rows as R type, and the next as B type. So we've got 3 signals that you're going to assign. The first one's done for you, the is I type, is I instruction. So these 2 bits here that determine which row we're on are instruction bits 6 and 5. So based on instructions 6 and 5, if for I type, if these bits are 0, 0, so again, using our constant expression notation, a 2-bit binary 0, 0 value. And again, just to make sure you've got the right tick mark, this is the single quote tick mark. And you'll come up with similar logic expressions for R type and B type. And again, you can pause the video, implement that, and come back when you're ready. All right, next up, I want to talk about a structure called a multiplexer. This is a very important structure in logic. So the operation of a multiplexer it's basically a switch. It's got a number of inputs, and based on a select, you're selecting one of those inputs to drive on the output. And I should grab my cursor highlighter. So in this case, we have 4 select bits, and one of them should be asserted. And based on the one that's asserted, we're going to select the corresponding input, which could be a single bit or a vector, and drive that as the output. And here I'm showing the way that this multiplexer structure is going to be coded in the tutorials in your starting point code and the syntax that you're going to use for the mux expressions. Here I'm showing a single bit mux, but you can do this with vectors as well. So the output of the mux, based on the select inputs, we're going to choose one of the input vectors. So this is the syntax, and you can read this sort of as a actually, this is the same syntax that you can find in C++ for a ternary operator, question mark, colon. I imagine most of you are familiar, but again, for those who are not, you can read this as if select 0, which of course is a 1-bit Boolean value, then select the input 0, which again can be a vector. Otherwise, if select 1 is asserted, select in 1. Otherwise, if select 2 is asserted, select in 2. Otherwise, select in 3. So this creates a prioritized select. Select 0 gets highest priority. So if multiple selects are asserted, the first one is going to win. And that means the default case, can it doesn't need to specify the select. If no select is asserted, it doesn't matter what the output is. We'll create this mux to always select the third input if none are selected. All right. So the next lab exercise, which is going to use that ternary syntax, is to decode the immediate field of the instruction. So some instruction types have an immediate field. We saw that add immediate instruction, which is operating on a register value as well as an immediate value that's specified in the instruction itself. So we saw basically an add 1 operation. That 1 value comes from the instruction bits as the immediate field. Also, the branch instruction is branching to a program counter target based on an offset value. That offset is provided as an immediate field. So I-type and B-type have immediate fields. R-type does not. So I've given you the expression here to start with for the I-type immediate value. So here we're assigning the immediate value based on the instruction type. If this is an I-type instruction, then use this expression. Otherwise, you're going to add the expression for B-type and the value that you would use for the immediate for the B-type, and then a default value of 0 if it's not I-type or B-type. So looking at this expression now for the I-type immediate, that comes from this table, from the RISC-V user's manual. And what this table means is that the first field of bits here down to bit 11 are replications of instruction bit 31. And we talked about the syntax for replicating bits using this goofy syntax with the braces, where we want 21 copies of instruction bit 31. So that's giving us this field of either 1s or 0s. And the remaining 3 fields here, actually for I-type instructions, these are actually contiguous bits. You'll notice that this is just instruction bit 30 down to 20. All right, these are all contiguous, and so instruction bit 30 down to 20. And then the outer brace here is for concatenation. So the outer brace and the comma are concatenating these 2 fields together to produce a 32-bit immediate value. And then you'll do similar for B-type instructions. So go ahead and pause the video and implement that logic, and you should see that once you implement that, the decode logic now shows proper fields for instructions as they're fetched and decoded. All right. All right, the next thing to implement for the decode logic is to pull out the various fields of the instruction. So we've taken care of the immediate fields. Now we're going to take care of the remaining fields and just pull them into their own signals. So for each of the fields here, RS2, RS1, Func3, RD, which is the destination register, and opcode, we're going to pull those into separate signals. So I've started you off with RS2, just using the bit extraction to extract bits 24 down to 20 based on this 24 down to 20 shown in the table. So go ahead and implement that for the remaining fields, and then come back. All right, the next thing is to determine when the various fields of the instruction are valid based on their instruction type. All right, so we're worried about R-type, I-type, and B-type. And based on the instruction type, different fields are valid. You can see for I-type, there's no RS2 because the second source is from an immediate value. For B-type, there's no destination register. So based on the instruction type, different fields will be valid. So I've given you the expression that determines when the RS1 field is valid. And so that's valid for R-type, I-type, B-type, all the types that we care about. And you'll create expressions for these remaining terms, the RS2 valid, RD valid, based on these various is, R, I, or B instruction. Alright, so pause the video, implement that, and come back when you're done.